If we open our computers, our smartphones, or any other electronic device, we'll certainly notice that there are always one or more electronic cards. In these cards, we will find small black parallelepipeds called integrated circuits. In this video, we will see how integrated circuits are made and why they are the basis of all electrical devices. The integrated circuit is an essential part of computing systems. The external layer is made of package, a plastic material, which isolates the internal components while leaving some pins uncovered on the outside. These pins connect the integrated circuit to the printed circuit board through the so-called wire bonding technique. Some wires, made of gold, aluminum, or brass, whose diameter only extend to microns, connect the pins to the DIE, a small semiconducting plate, usually made of silicon, upon which the integrated circuit board is realized. The latter can be made up of millions of basic electric components, such as transistors, diodes, capacitors, and resistors. The DIE is realized thanks to a process called miniaturization, which allows it to be more reliable, to have better performance, and finally, smaller dimensions. The term integrated refers to the presence of a high concentration of basic electric components in a small area, whose job is to process the incoming signal. The scale integration of an integrated circuit gives an indication of its complexity, roughly measuring how many transistors are contained inside a circuit. The process of making the DIE is very complex. It is made of silicon, which is the second most abundant element on the Earth's crust after oxygen. It is easily found in the sand, but since it must always be melted to other materials in order to become a semiconductor, several processes are required to obtain these chemical properties. Firstly, thanks to sophisticated technologies, it goes through a purification process that creates thin sheets of pure silicon called wafers.
Through the photomask in special exposure machines known as steppers. During this process, coaster-sized areas of the chip template, known as reticles, are used to transfer the complex geometric patterns of the circuit design to the silicon wafer. The exposed area of the chip pattern is developed, revealing the layer of oxide below. The unexposed part remains as is, protecting the layer of oxide. After this, the exposed layer of oxide is etched off in the areas that have been developed using wet or plasma etching. With plasma etching, special gases bond with the substrate to be removed in the reaction chamber. This enables microscopic layers to be removed in the windows that were exposed and developed in the previous step. Once the photoresist residue has been stripped and the wafer has been cleaned, the wafer undergoes further oxidation. Electrically conductive polysilicon is deposited on this insulation layer.
In the next step, called lithography, the silicon disc is coated with photosensitive material to expose the various wafers to ultraviolet rays. The exposure is obtained by using a mask on which the design of the microcircuit is printed. A lens concentrates the drawing in order to make it smaller. This process is repeated many times, creating several layers. After this step, the areas that have been exposed become soluble and are removed from the wafers. In this way, the whole intricate circuit can appear. After that, atoms of different elements are added to the exposed parts. This operation is called doping. In this way, thanks to the presence of impurities in its crystal lattice, silicon becomes a semiconductor. Subsequently, the material obtained is washed. A protective layer is placed above, and finally, a copper coat that fills all the spaces left is applied, making the DIE smooth.
Individual chips are usually sawed out of the wafer. The chips are not lined up flush with each other on the wafer because tiny parts of the wafer splinter off during the sawing process. A certain amount of space, known as the scribe line, is always left between the individual chips. Test structures are also integrated in the space between the chips and used to take measurements immediately after production. These test structures are destroyed during the sawing process. The size of the resulting chips typically varies between 1 square millimeter and a few square centimeters. The final stage of fabrication is assembly. Here, the individual chips are placed in a package and terminals are attached. The result is a finished semiconductor device, which can be mounted on circuit boards using different types of terminals. Over 1,000 connection contacts can be realized. Here are some examples of ready packaged semiconductor components. Special larger packages are used for power semiconductors, intended for applications such as trains, electric cars, solar panels, and wind turbines. These power semiconductors are designed to switch electrical currents of up to several hundred amps and voltages that run into the thousands. Switching at this level generates high temperatures, and this heat has to be dissipated via cooling areas integrated into the packages. Here you can see some fully packaged power semiconductors. If we compare today's microelectronics with human hair, we can see just how small these devices are. The equipment used to check components and analyze defects is just as precise. These high levels of precision and quality are essential at every stage of the workflow, from the production of silicon boules through the cleaning room fabrication to quality control, in order to deliver these tiny building blocks that have such a big impact on our lives, today and in the future. After all, demand is rising for innovative semiconductor solutions that make life easier, safer, and greener. For technology that achieves more, consumes less, and is available to everyone. Microelectronics is the key to a better future.